Welcome to Inorganic Chemistry. On this lecture, we will look at the chemistry of the group 4A elements. So we've seen a guiding framework to our tour of the main group elements. We've looked at the alkali metals, the alkaline earths, and the group 3A elements. Now we're looking at the group 4A, which again do not have a family name, and that may be again because they're so different from one another, but actually there are a lot of ways that they're the same. Now the main notable element in this group is carbon, which, as we all know, is the basis of organic chemistry. That, of course, wasn't always known. Originally, Berzelius, in the beginning of the 19th century, defined organic compounds as those that are derived from living tissue, and it was thought that organic chemistry was somehow different than inorganic or non-living chemistry. It wasn't until the 1830s that Wohler determined that organic chemicals can be made from inorganic chemicals. He made urea, and so we realize that there's not something special about organic versus inorganic chemistry. What does define organic compounds is that it contains carbon. Now, there are also inorganic forms of carbon, and the elemental forms of carbon come in different shapes, different phases, and these are called allotropes. So we'll spend on our next lecture series, we'll look at some special topics from main group chemistry, including the allotropes of carbon. Another unique aspect, again, carbon's the first member of the group, and so it is unique from the rest of the members of the group, is that its ability for catenation, or to form bonds with itself, and in particular form chains and rings with itself. And this is a property of carbon, is again what gives the variety and diversity of organic chemistry, which is why living organisms are based on it, and why we have a whole separate subdivision of chemistry devoted to the chemistry of carbon. So sometimes in science fiction we talk about, well, why can't we have living organisms based on another element, say silicon, which is in this same group? And it's because of the uniqueness principle, but let's look at thermodynamically why. So let's compare the carbon-carbon bond to the silicon-silicon bond, and we see that the carbon-carbon bond is stronger, which is going to make for a more stable catenation. The carbon-hydrogen bond is stronger than the silicon-hydrogen bond. So again, if we have hydrocarbons, we can make more stable compounds than the silanes, which would be the hydro-silicon analog. On the other hand, what happens if we react with oxygen, which is of course very prevalent in the air? Well, the silicon-oxygen bond is stronger than the carbon-oxygen bond. So actually we wouldn't expect this, because we'd expect these bonds to be stronger due to the shorter sigma bonds. These atoms can get closer together, the atomic orbitals can overlap better and get better covalent bonds there. Silicon's larger, can't get as close, so you'd expect the same problem here with silicon oxygen as opposed to carbon and oxygen, but it's stronger. Why? We'll see that on the next slide. A new addition to our guiding framework called the p-pi-d-pi bonding, which becomes important at this part of the periodic table. What this describes is how the p orbitals from a period 2 element can overlap with the d orbitals of a period 3 element. Now the d orbitals in a period 3 element, the 3d orbitals are not occupied at this point because they're too high in energy, but as we go across the period, they get lower and lower energy to shielding effects, and so this 3d orbital becomes more and more available. You just have to add less energy to access it. Meanwhile, these p orbitals are getting bigger as we go across the period 2. So now we reach a point where these p orbitals from period 2 can overlap with the d orbitals of period 3. This is actually experimentally shown if we compare trisilylamine to trimethylamine. Now we're very familiar with trimethylamine is like ammonia. We have a trigonal pyramidal geometry because of the steric number with this lone pair here. We'd expect the same thing because we just go down the group and we put silicon here instead of carbon, we would expect the same thing, but what happens is that this p orbital on the nitrogen is able to overlap with the d orbitals on the silicon atoms, making kind of a partial pi bond. So instead of a trigonal pyramidal shape, we get a trigonal planar shape in the trisilylamine. And we'll see this p pi d pi importance as we move along in our tour of the periodic table. What about the rest of the elements in group 4a? So germanium is amphoteric, so germanium oxide is kind of like aluminum oxide. Tin has been known since ancient times and is a metal used for plates and used in alloys like bronze when you add it to copper. It's used in solder when you add it to lead, and it's used in pewter when you add it to antimony and copper. Okay, so lead. Well, we see the inert pair effect. Of course, lead, metal, plumbing is the Latin root of the element, so it's again known since ancient times. We've already learned about the inert pair effect. So here, for example, the halides, tin dichloride or tin 2 chloride is an ionic compound and is stable. It's a mild reducing agent, so it will react to go all the way to tin 4, but tin tetrachloride turns out to be a covalent molecule, which we can understand if this is plus 4, then it has a high charge density and will polarize those chloride ions to make a covalent bond, as we've seen in other molecules. What about lead? Lead is ionic. Lead chloride, the lead halides, are classic insoluble when we look at solubility rules, so that's ionic, and you see that's plus 2. We can make the plus 4, lead oxide, for example, but that is a very good oxidizing agent and is used in lead acid batteries. So that concludes our tour of group 4a. We'll look at the next group, the nicogens, in the next lecture.